Has anybody here seen this? That the bastard reef cuts down through the Marinsky Reef. Well, no, I'm not saying they're lying, but you know, when you're underground, it's dark. You make some sketches. You know. Anyway.
Hoe do I get back? Pointer. Okay, how do I get rid of this now? There we go. Thanks. Okay, good afternoon, everyone. And we'll be continuing with the Bushveld. And today the talk will be on the constraints on the neodymium isotopic composition and the nature of the last major influx of magma into the Bushveld complex. Okay, so Boral 771 was also sponsored by Impala Platinum towards the ICDP, and I had the privilege of doing my PhD on one of these borals. So Boral 771 was drilled in the central sector of the eastern limb of the Bushveld complex. It is colorated in the main zone and extends down to the Marinsky footwall. For those of you that is not quite familiar, the peroxenite marker is a thin autopyroxene-dominated marker horizon, and it is thought to believe to be the last voluminous influx of magma due to some mineral reversal in mineral compositions, as well as breaks in strontium isotopic compositions. Okay, so in Boral 771, 45 samples were taken, of which 21 samples were analyzed for strontium neodymium isotopic compositions. The samples were taken in 10-meter intervals, and closer to the vicinity of the peroxenite marker, they were taken in 1 meter to 0.5 meter intervals. From the simplified lithological log, you can see that the lithologies that were seen is your gabbronorites, your leucogabbronorites, mallogabbronorites, leuconorites, leucogabbros, peroxenites, anorthosites, and then also some IRAP samples. So the aim of the study was to constrain the neodymium isotopic composition and to the nature of the magma that was added at the level of the peroxenite marker. So this was done through whole rock strontium neodymium isotopic compositions of the rocks that went across the peroxenite marker interval, as that was sampled from Boral 771. So as Bob said 2 days ago, the main zone is quite boring. The lithologies consist mostly of plagioclase and then also low calcium and high calcium pyroxene. So myrmekite was a common structure that was seen in the gabbronorites, and it occurred quite closely to the plagioclase contacts. In the peroxenite lithologies, inverted pigeonite, quite beautifully, was quite often seen, and it decreases towards the peroxenite marker. At about 30 meters below the peroxenite marker, the inverted pigeonite was replaced by primary autopyroxene as the low calcium pyroxene. In the peroxenites, you can also see that the clinopyroxene often showed these chiller structures, and intercumulus plagioclase was also often seen. In the peroxenite marker, less than 1% inverted pigeonite was noted, and then the autopyroxene also contains some clinopyroxene plebs. Okay, so the plagioclase content varies across the studied interval, and as you move from the bottom, the anorthite percentage increases towards the base of the peroxenite marker. Localized increases or decreases was usually associated with pyroxenites or the IRAP samples that were present. The iron percentage decreases at the base of the peroxenite marker, with an increase towards the top of the studied interval. And then the peroxenite also showed some variation across the studied interval, with the magnesium number also showing a generalized increase towards the base of the peroxide marker. Just below the base, the magnesium number decreased, and then you see little variation towards the top of the studied interval. Kleiner pyroxene is not shown here, but parallels that of the OPX. Okay, so the heavy rare earth elements show little fractionation. Most of the samples you can see exhibit positive europium anomalies with values between 1 and 10. Some of the samples do show negative europium anomalies of 0.7 to 0.9, and these were usually the peroxides and the IRAP samples. Okay, so zircon was fairly constant. Fluctuations were usually also associated with the peroxides and also with the IRAP samples. Zircon values was on average lower than that below the peroxide marker. Then the strontium aluminium oxide compositions as a function of differentiation of plagioclase showed a stepwise decrease towards the base of the peroxide marker. The chrome-scandium ratio as a proxy of Kleiner pyroxene differentiation shows very little variation in this vicinity, with an abrupt increase in the same area where the inverted pigeonite was replaced by primary autopyroxene. Okay, so for the isotopes, the initial strontium 87, 86 ratios showed an overall decreasing trend towards the base of the peroxide marker. Then an abrupt increase is seen at the base of the peroxide marker to a local maxima of about 0.7079. The epsilon neodymium values show some fluctuation below the peroxide marker. And then at about 1.82 meters below the peroxide marker, the value increased from -6.7 to -6 at the base of the peroxide marker. From the base of the peroxide marker, the epsilon neodymium shows significant intersample variation, and that seems to be the norm going up the studied interval. Okay, so in order to constrain the neodymium isotopic composition of the magma that was added at the level of the peroxide marker, some additional parameters needed to be constrained. So one of them was to identify or to get the neodymium isotopic composition of the resident magma, as well as the mixed magma. Then also to identify the neodymium content of the resident magma and the incoming or mixed magma, and then also to find out what is the ratio in which these magmas were mixed. And this could be determined from the strontium isotopic data. So using these two-component mixing equations, the mixed magma was used, or the two-component mixing equations was used to constrain the diagrams. So for the mixed magma, initial strontium 87, 86 of about 0.7073 was taken from Creer, and the epsilon neodymium value of -6.43 was taken from Tanaka and Masura. So it's important to note that this epsilon neodymium value was only from one sample that was available from the upper main zone. Okay, so for the following three diagrams, the resident magma was taken as an epsilon neodymium value of -7.01. and an initial strontium value of 0.7084. And this was taken from Meyer's work in 2000. So for the first diagram, the initial strontium value was taken as 0.7063 from Cawthorne, and the strontium and neodymium content for the resident and the incoming magma was taken to be quite similar. This constrained an epsilon neodymium value of -5.9. Then for diagram B, the incoming magma was taken as an initial strontium value of 0.7067, which was taken by Van Tongeren and Matthäus. And the incoming magma strontium content was taken to be higher as that of the resident magma. And this constrained an epsilon neodymium value of -5.9. In diagram C, The incoming magma was again taken as 0.7067 from Van Togher and Matthijs, and the incoming magma strontium content was higher than that of the resident magma, and the neodymium content of the incoming magma was also taken as to be higher as the resident magma. These strontium neodymium content values was also taken from Van Togher and Matthijs. For this diagram, it constrained an epsilon neodymium value of -6.1. So what do these mixing diagrams tell us? First of all, none of the mixing models provide a particularly good fit for our data. Therefore, we propose that this is the result of minerals crystallizing from the resident and the incoming magma, and that it was incorporated into individual rock layers. Rocks from the Bushveld complex representing mixtures of minerals accumulated from different parts of a stratified magma column is not entirely novel. Okay, so this was also shown to be the case for work by Breivik for the Merensky Reef, as well as Seabrook for the Merensky Reef, as well as Bordeaux for the neritic from locks from the anorthosite in the upper main zone, as well as across the peroxenite marker by Cawthorne. So the following diagram was taken from the first mixing model with 2 additional mixing curves that was added. So as you can see for these for this diagram again, the 0.7063 was taken for the initial strontium value and -5.9 for the epsilon neodymium. You can see that most of the data is now constrained by the diagram, except for 2 points that we believe to be aberrant. So the assumption for the curve C in this case was that the plagioclase crystallized from the resident magma with strontium concentration of 457 and neodymium of 1.4. And the kleiner pyroxene crystallized from the incoming magma and with a strontium content of 11.6 and neodymium of around about 9.2. Assumptions for curve D was that the plagioclase crystallized from the incoming magma and that the kleiner pyroxene crystallized from the resident magma. So the autopyroxene was omitted for these calculations for the sake of simplicity, but would have had little effect on the strontium neodymium isotopic compositions of the mixed magma due to the low concentration or low abundance of both of these elements in it. So as you can see from the diagram, if we used an epsilon neodymium value of -6.1, not all of the data could have been constrained, and therefore we propose an epsilon neodymium value of -5.9. This would imply that the neodymium contents of the incoming and the resident magma must have been rather similar, in contrast to what has been proposed by Van Togher and Matthijs in 2013. So where and how did mixing take place? Okay, so most of the models for the development of the peroxenite marker assumes that mixing of the resident and the incoming magma took place in a confined of the magma chamber, that the incoming magma was added gradually to the chamber and then either forming a layer that was stabilized at an intermediate level within a stratified magma column before being thoroughly mixed with the resident magma, was shown to be the case by Cawthorne. Or it could be as numerous small injections that became homogenized, cooled, and partially crystallized between these successive injections. That was suggested by Van Togher and Matthijs. We propose that the rocks across the peroxenite marker interval may represent mixtures of minerals and melts that underwent mixing during the ascent from a subcompartmentalized staging chamber. In this case, in this type of scenario, you will typically have the rocks that's below the peroxenite marker. That is then the product of repeated intrusion of a contaminated crystal mush, and then with a strontium value of around about 0.7084 and an epsilon neodymium value of around about -7.01. As it ascends, it mixes with a crystal-laden magma with a unique strontium isotopic composition of around about 0.7063 and an epsilon neodymium value of -5.9. That is then resident in a subcompartmentalized chamber. Okay, so the magma that was responsible for this observed isotopic shift that we see across the peroxenite marker interval thus had a unique strontium and neodymium isotopic composition, as you can see from the diagram, where this represents the upper critical zone and this the main zone. The pink is from this study, and here you can see the suggested composition for the magma that was added at the level of the peroxenite marker. So this argues against the model of Sharp, who attributed the peroxenite marker interval to the mixing of occurring between the underplated main zone magma and the displaced resident magma of the upper critical zone. So in conclusion, the magma that was added at the level of the peroxenite marker had a unique strontium and neodymium isotopic composition. Initial strontium 8786 of around about 0.7063 to 0.7067, and an epsilon neodymium value of around about -5.9. This records evidence for a lesser degree of crustal contamination compared to that of the resident magma. The mass of the incoming magma was approximately equal to that of the resident magma. The peroxenite marker interval records evidence for the accumulation of minerals derived from both the resident and the incoming magma. This could be explained by the mixing of minerals settling through a stratified magma column that was shown by Hawthorne et al., or potentially through the mixing and intrusion of a mixing of crystal-laden magma with unique isotopic compositions from a subcompartmentalized chamber during ascent, as shown was to be the case by Roelofse and Ashwell. Okay, thank you.
Okay, thanks. Remember there was Marianne talk, she showed us two thin sections. One formed example of the rocks formed from the crystal mash, where all minerals were ideomorphics and just touching each other. Another example of the rocks which formed along the margins and in situ crystallization, when all minerals kind of into touching each other and growing into one another. So I wonder if you have textural, if you look at the texture to make, to confirm the idea that, to have evidence, textual evidence to say that in your case, that was a crystal mash, basically. Individual crystals collecting on the chamber floor. What do your texture tell you? Thanks.
Yes, I don't think we saw any textual evidence for this, but I think it's hard, you know, to explain this type of where you've got crystals that shows both from an incoming magma composition and from the resident magma composition, that it could have happened just by density settling or something like that. So I think that was the best idea that we could have came up with.
I understand it's chemical evidence. I'm asking the textual evidence.
No.
Can we confirm it by texture? Okay.
Thanks very much. That was great. The one comment I have is that if you have it, the idea of the crystal mixing of seems to me to be a very good idea at this point. Was it the resident magma was the main zone magma, which had some residue there. We calculated that the new magma that came in was about 2/3, I think it was in that order, 60% new magma and 40% of residual magma in the chamber. But once that magma had got in there, whatever the mixing process at that contact, it mixed completely and stopped, because that initial ratio for strontium is then constant from the peroxenite marker to the roof. So that entire thing is then a closed system magma chamber. And that's it. So this is the only place in the Bushveld complex where you can actually see continuous differentiation processes happening, not mixing of new magma or anything, just continuous processes of differentiation. Thanks.
Hi. I'm just wondering, does your data not actually provide a fairly strong case, irrespective of what other folks have presented in the past? But you've got your residual and your additional magma both actually having very similar, as in like minus 6.5 epsilon. Strikes me that it would actually be a lot easier to just mix horizontally on your isotope diagram plots there, rather than trying to mix in something that's got two different epsilon needed. But you've actually got a good case to make. That's what the situation really is.
Okay. Thanks.
Can I borrow you for a minute? I'll show you a better answer for your question. I have no problem with the bastard coming in later. So we got distracted by Wolf there. Where's need? Because I just need, I don't want it to be solid above, right?
Sorry, once again.
I don't want it to be solid above my pulse, above my Morensky.
You don't want to be solid. But
No.
if it's sealed, how?
No, it just becomes, I need a contrast of temperature, and the rock above is cooler than the new pulse. Hang on a second. Because it's hot. I mean, it's a resident magma that's in there, right? So it's going to be, if a new pulse of liquid comes in. So when a new pulse comes in, whatever was there already is going to be cooler. So that's the thermal profiles, like the red. So the new pulse has got to be hotter than whatever was already there, because it hasn't had time to cool yet.
Are you saying that is it basal flow or is it sealed? That's what I do.
Well, I don't care.
Yeah, but it's principle, you know, if it's a basal flow, intruding below, there is the melt rating, then bastard reef, then it's no problem.
That's right. Well, so I'm saying it's a lateral emplacement of magma. If the difference between if you're saying a sill is intruding into salt, then it's not a sill. I don't want it to be solid.
Yeah.
So then you can say it's a basal flow.
Yeah.
Yeah. So that's,
But I don't have problem with it.
Okay.
But you say sill.
well, then I explained what I meant by that, like that you've got a transient crater, a transient cavity floor, transient whatever it's chamber floor,
So
where
then,
you've got 60% crystals here. So that's where it chooses to come in
so
on,
then this is a pile and that is a liquid then.
with crystals in it, but
with
just not as
crystal.
many.
Okay.
I mean, that would depend, how many crystals there are in the top part would depend on how long it's been since the last pulse.
Well, that's perfect, absolutely. So
So-
basically, that's what I was proposing, basic
Okay.
flow. But when it's a seal, that's
Yeah.
already.
So that's what I
requires a
wanted
lot
to
of
make
questions.
sure you were
Okay.
clear that what I
Okay.
didn't mean. So,
Okay.
okay.
Thanks.
So-
Thanks.
Yeah.
Steve, symmetry you're talking about, this.
Yeah.
So you're saying the highest concentrations of PGEs are in the.
Yeah, let's see, let's go back. No, they're at the they're at the contacts.
Okay, so what's this symmetry that you?
Well, that's the temperature profile. Oh, the symmetry, that like,
And then
yeah,
that's
yeah, yeah.
what's your idea that this is intrusive.
It's,
Okay,
that's the Aldred things.
yeah, so that's the measured sort of.
It's this stuff. It's the fact that I realized I should have drawn like a schematic. A stylized version, so people stop looking at my actual data and look at
There's a pen and
the
paper.
bullshit version.
Okay.
Maybe stop the recording.